Hello, welcome to AutoAir Past and Future. AutoAir was a 5G testbed project, partly grant funded by the UK Government's Department for Digital, Culture, Media and Sport. The project ran over 2 years. The first year was mainly about building the network, which was reflected in the makeup of the consortium. During the second year, trials were conducted using the network for the automotive sector. During this presentation, we're going to hear from representatives of a number of the key members of the consortium, starting with an introduction from Ian Smith from DCMS.
Good afternoon. My name is Ian Smith. I am the Programme Director for the DCMS 5G Testbed and Trials Programme. I'd like to welcome you to this video presentation on behalf of the AutoAir 5G Testbed. In 2016, the Government announced over £1 billion of funding to boost the UK's digital infrastructure. 5G is a critical component to delivering the next generation of digital infrastructure. Government has invested in a national coordinated programme of 5G testbed facilities and application trials. The programme has been running projects across the UK to deploy wireless infrastructure and test 5G technology. In March 2018, the Government selected AutoAir as winners of the first funding competition from 5G Testbed and Trials programme, which was designed to explore the development of connected and autonomous vehicles and how 5G connectivity solutions could be used on road and rail transportation. Each testbed has been supported and received between 2 and 5 million in government grants. This is matched from the consortium and the private sector, which means we have a total investment in phase 1 of over £40 million. Due to the success of the AutoAir project, we extended to learn more about the benefits and learnings, and I'm pleased to say that in a challenging 2-year timeframe, the project has delivered some really significant outcomes. We have proven the viability of neutral host small cell networks for 5G, both technically and economically. This is validated by the fact that Telefonica, Millbrook and DCMS are continuing their collaboration after the end of the AutoAir project. Blue Wireless, and a key partner, have made huge progress in the development of their mmWave 5G technology for communicating with high-speed trains, have got increased commercial traction as a result. They've shown sustained throughputs of 1.6 gigabits per second with continuous handover to vehicles moving at 150 miles per hour. That was an impressive day out. I enjoyed that on the coach going around, watching the McLaren zooming around with that high-speed connectivity up and down. Very impressive. The 5G Innovation Centre at the University of Surrey has obtained validation of its innovative 5G beamforming algorithms in a real-world environment, advancing the UK's position as a leader in 5G technology. AutoAir have built a sustainable testbed for the automotive sector that is already seeing commercial use. I am very proud of the work that has been done here. I'm very excited about the outcomes from the trials, and I look forward to seeing the applications moving forward. Thank you.
This is Peter Stoker. I'm the Chief Engineer for Connected and Autonomous Vehicles at Millbrook. And this is a series of slides showing the AutoAir involvement at Millbrook and how the network was developed and how we installed it within the Proving Ground. First slide you can see is something that I showed way back in 2017, which was really a 2-slide pitch used at KTN events. And this one we used at the 5G Testbed and Trials competition briefing event in London. So the first slide essentially shows Millbrook, 100% British, impartial, independent, safe and secure in different locations and part of Spectris PLC. So you'll see the bottom left corner is where we are pitching and what date it was. So moving on. So we had 2 significant government-supported testbeds on site at Millbrook. The first one, calendar-wise, was partially funded by the Centre for Connected and Autonomous Vehicles. It is a partnership in itself with the UK Atomic Energy Authority and essentially sets up the UK's controlled urban testbed for connected and autonomous vehicles. Within this deployment, we had some initial connectivity ideas where we would put together a series of enabled infrastructures being masts, power and fibre, and essentially completing a lot of the civil work with a view to customers and infrastructure owners bringing their devices to put on top of that infrastructure. However, the 5G Testbed and Trials program came along. We pitched at the event and we were introduced to the guys from Airspan and asked would we like to be the location for the AutoAir project. And from small 2-slide presentations, then mighty oaks tend to grow. So in March 2018, we announced the participation of Millbrook in the consortium as the location for the 5G test infrastructure. Things moved quite rapidly, and in July, we hosted an inward visit from DCMS to look at some of the initial ideas and some of the advanced devices that were likely to be deployed. A very successful day in the high summer of 2018, and from that really we started to develop the site in earnest rather than just planning. Millbrook, as you can see here, is a 700-acre site, and in the summer of 2018 we had no connectivity at all, apart from a mobile operator macro cell which is located here, which gave us good coverage across the site but only on one network. And if you weren't on that network, then it was a real issue coming to Millbrook to test in terms of its connectivity. So part of the AutoAir deployment is described in the following series of overlays. So firstly, we had to provision for power and fiber around the site. Some of this was covered in the CCAV testbed, others was additional to AutoAir. So we covered the site with 19 miles of fiber, around 30 kilometers, set up into different circuits to provision connectivity to different areas of the site. On the flat area of Millbrook, which you can see here laid out, we added a lot of cells, small cells in the flat area and linked them together in the network. And this was the first part of the network was deployed at launch in February 2019. Going on from there, we added cells and sites in the hill route at Millbrook. So this is the hilly area, so-called. And further on, we then added the mmWave sites. These were actually present at launch as well. So the mmWave sites went on to be something really quite significant and given us some of our biggest numbers. Small detail added on into here was the provision of mesh sites in the hill route to simulate urban connectivity. So 5G might be an awful lot about networks and infrastructure and technologies, but for Millbrook, 5G initially was all about digging. And you can see here we picked a good dry summer to do this in. Actually, the site is on Bedfordshire clay, which in high summer turned to the consistency of concrete. So it was quite hard going, but we didn't have any rain interruptions, which was a good thing. And we managed to pull in all our ducts and bases and trenches and concrete in at the right sort of time frame to meet the program demands. Once some of the sites were in place, then we looked at fine positioning rather than what was on the radio plan, because we had to work with the architecture that we had, the topography that we had, and the tree lines that we had at Millbrook. Also, we had to look at the safety considerations of siting masts in safe locations, so not on the outside of bends where test vehicles could leave the track. It is a test track after all, and we didn't want any collisions with the surrounding telecoms infrastructure. So we tried to keep it as safe as we possibly could be, and this was a good part of working together to refine those positions. In February 2019, we hosted a great launch event where we invited all kinds of people from industries, different industries, from transport and also from the technology sectors. Had a series of speakers, some really good high-level speakers, and ran some demonstrations around the high-speed bowl at Millbrook. So this is what this slide is from. There were some great video feeds from that went on to make BBC News and lots of publications, and we've used it in dissemination events ever since. So there's a lot written about this demonstration day, which I won't repeat here. As a result, here we can see a selection of the small cells that are positioned around the site at Millbrook. The metal masts are essentially on the flat area that I explained earlier. The wooden posts we deployed into the hill area, and actually they blend very well into the agricultural background. The masts are tiltable for easy access. So again, if any devices are changed or people want to bring new devices, then they can be added to the masts in a fairly straightforward way. So one of the use cases we've put the system to at Millbrook is live collection of data. And as you can see here on the screen, this is a speeded up recording of one of our engineers driving one of our connected vehicles around the site. So previously, Millbrook has fitted data loggers to lots of vehicles. They have recorded the data and it's been available the day after or the same day for analysis. However, if there are any issues with sensors or test routes or speeds or something like this, then again, the whole test has to be repeated because the engineer has no sight of what is actually going on real time on the vehicle itself. So using the AutoAir network, Millbrook have developed this in-house ability to look at the data live, and we can stream this straight to the engineer's desktop in the office. We can show it to customers in a confidential conference room, and obviously we can record it as well. So this particular example is driving around all the tracks at Millbrook, and essentially we're showing on this screen accelerator, brake and steering, also the gear, the vehicle speed, the battery condition because it's a hybrid, and the engine speed and engine torque. It will drop to 0 because it runs on electric drive occasionally. So in this way we can do plausibility checks on sensors, and we can keep a live eye on vehicles that are driving around. We can raise any flags if there's any issues also. So this has been very useful to us and now forms mainstream vehicle testing. So we're doing this on durability vehicles and on customer measured vehicles as they drive around on unique tests. Some of the other use cases we've proceeded with, this particular one was released in March 2020. This is the O2 Smart Ambulance trial that was done at the end of 2019 at Millbrook. And this is a good collaboration from O2, from Samsung, from Visionable, and looking at getting live high definition data over a high bandwidth connection to a remote hospital consultant to make diagnosis and talk about treatment plans. So Millbrook was the ideal location for that, and AutoAir the ideal network to run that on to demonstrate what could be possible in the future. The second piece is coming out, which is now a great piece of video from the Institute of Engineering and Technology, demonstrating again the autonomous village that we have and also the highly connected vehicle, and explaining an awful lot on the background about how that is set up, what it does and how it benefits. So we can circulate a hyperlink for that video as well. Millbrook will probably release that in April of 2020. So these use cases have been the basis of some of lot of the dissemination activities that we've run over the past couple of years. We will continue to use them and grow the use case library at Millbrook, and it's now ready and available for customers to use on a commercial basis. I think overall, from a Millbrook point of view, this has been a great addition to the capabilities that we have on site. It has a great addition to the technical library of devices and things that we can interact with. It's brought us a huge amount of new customers from new industries, and it's all been possible by the great collaboration we've had between all the partners in AutoAir, great support from government as well, and it's going to be really exciting going forward into the future. So thank you very much for your time, and have you enjoyed it?
Hi everybody, this is Paul Senior. Just wanted to talk about DCMS and Airspan and what we achieved through the DCMS's 5G Testbed and Trials project, AutoAir. So let me take you through kind of a summary of what we believe we achieved and what we think is a sustainable legacy that we give. So, really just wanted to chat briefly about what Airspan and DCMS actually built. We'll talk about, the hyperdense network, talk about, all the things that the benefits that the project gave. What did we achieve? How do we accelerate UK R&D? All the individual technologies and improvements that were made. And then finally to talk about what the sustainable legacy is. So let me quickly move through the deck here. So what did we build? So I think the first thing to remember is that we went to a real greenfield site. There was extremely poor mobile coverage available at the Millbrook Proving Ground. There was basically just one EE macro cell. And what we built there over basically the first 12 months of the project was a hyperdense small cell network. And the final counts were 86 GNOBs on 39 locations, 22 mmWave sectors around the high-speed bowl done by Blue Wireless, and 23 mmWave backhaul links across the thing. We actually laid down 19 kilometers of fiber to connect 23 of those sites. Actually, subsequently, fiber's been built out virtually to every location and provided, apart from the off-road course, pretty much complete coverage of all of the test tracks that Millbrook has. And you know, as you can see here, the small cells on Millbrook have actually, they are very small cells and very difficult to see. That gives you kind of an example of what they look like. This is around the hill route. And at Millbrook, we built two types of infrastructure. One infrastructure was in the 2.3 gigahertz band, and one infrastructure was in the 3.5 gig band, which was our focus on 5G. This was a snapshot from the AutoAir demonstration day back in February, I think it was February the 12th, 2019, where we basically did a series of active demonstrations to show the capabilities of the network. And during that day, we put lots of people around the track in coach loads to show some of the interesting use cases that can be achieved when you deliver hyperconnectivity to connected and autonomous vehicles. And one of the key showcases was to really show that if we can in real time share information between connected autonomous vehicles, we can make better choices. If you like, you can see around the bend ahead, which is the example showing on the screen here. So what did we achieve? Well, I think the key thing is there were lots of lessons learned. You know, constructing the network was not trivial. We did this across a winter period mainly, and it was pretty difficult, but it was possible to do that. We definitely, you know, we'll talk some more about this in a little bit, you know, accelerated the R&D programs, both inside of Airspan networks and dense air. We built a prototype GNOB, which was used as a platform to learn many things about the commercial products that Airspan networks will subsequently offer in the 5G space. And that was a direct, you know, that took technologies from people like the University of Surrey and their beamforming technologies and married it with the hardware and software platforms that Airspan Networks does, and that was a really big win. We built a neutral host core. A neutral host core is something where we constructed a network whereby you could have a single network providing both public service and private services. So private network connectivity for manufacturers of CAVs and subsystems to come and test with, and also a public network that, as we'll explain, is something that O2 then built out. You know, using millimeter wave for deploying Open RAN backhaul, and Open RAN backhaul is something I'll talk about just in a moment, but it's next generation 5G architectures where we disaggregate and break up a traditional base station GNOB, ENOB into constituents parts. We showed that, you know, we could use those millimeter wave technologies to build networks in new ways, ways that we're going to increasingly leverage as, you know, as 5G comes, as 5G infrastructure is built out in the UK and elsewhere. And again, one of the, you know, best days of the project was when we all got together and basically managed to do a whole series of demonstrations to, you know, to a very large audience from both the CAV industry and the telecoms industry, and showing how if you put these two industries together, what synergy there is to show, you know, we've got some technology, connectivity technology that, you know, I think we opened the eyes of many people that day to show what was possible. So just finally, to kind of wrap up here in terms of, you know, the kind of debrief here about what we achieved. What is a sustainable legacy? You know, I think the first key point is that AutoAir, particularly, I think, put 5G on the map for the UK. I think, you know, there was massive interest in the things that we did, the proof points that we showed. We had a very significant presence at Mobile World Congress in 2019, and you know, it really turned the spotlight of attention on the 5G about how you can use 5G innovation, to make a whole bunch of new use cases and industry segments kind of breathe life. If I come back to what Airspan achieved, the AutoAir project was definitely the genesis of our next generation's 4G and 5G RAN, which are all built around open architectures and virtualization and network intelligence. And, that, certainly was a direct input to, product development efforts that go on around our Open RAN portfolio. And Millbrook is definitely an example of Open RAN deployment, seriously ahead of the curve about building a network in this way, rather than the traditional monolithic macro cell approach. And there has been direct benefit in the software development space for Airspan, and direct impact on Airspan's ability to bring products to market in the 5G space. And Airspan Communications Limited has been in the UK for 25 years. It's a little known secret. It goes all the way back to 1994, and this project certainly accelerated the development of 5G infrastructures and 5G products, here in the UK. So it was a direct benefit. And I guess the final piece here is of course, we're not finishing really, although the project came to an end this week. We are focused on making a sustainable legacy. So we're not throwing away and tearing down the network. We're doing the opposite. We're actually deploying over the top of this network a new 5G commercial infrastructure, taking away the prototypes and the other pieces and leaving a very, very high performance sustainable network. And we're doing that in partnership with Telefonica O2. So we'll have the scenario where this network simultaneously provides a private LTE network for Millbrook for its customers, and simultaneously also advertises O2's PLN-ID, so it becomes part of O2's public network. And that's completely unique. So that is a clear sustainable legacy out of this project. So, in conclusion, this was an amazing collaboration that we did with a whole bunch of companies. In fact, it is quite remarkable how well we all worked together as a team. There was massive amounts of innovation that occurred during the project. There were new kinds of conversations that we had, brokered by Millbrook itself, allowing us to see and, get kind of many more interactions between both the COV industry and the telecoms industry. And it led to this unique partnership at the end of the project, whereby O2, Millbrook and DCMS will continue to build, operate and maintain this network, over the next 3 years at least. So with that, I'll stop and say, yeah, it was a great experience, and certainly, speaking for DCMS and Airspan, we're very keen to continue this kind of arrangement in the future.
So, good morning. My name is Mark Barrett. I'm with Blue Wireless Technology. We're one of the partners in the AutoAir project, and this presentation is concerning our contribution to the project regarding 5G mmWave for transport applications. Before I start, just a few words on Blue Wireless Technology. We're UK SME. We're based in Bristol. We were founded in 2009. And we focus on deep technology development for mmWave applications, particularly with regard to the 57 to 71 gigahertz license exempt spectrum, which is a spectrum that we exploit using the IEEE 802.11ad standard. We're based in Bristol, as I've mentioned. We have 85 staff. We also have an office in Hyderabad in India doing software and verification, and business development activities in North America and Japan. We provide 3 streams of business. We develop advanced baseband system on chip silicon. We license our technology to many customers, notably Renesas IDT, as regards their RWM6050 modem, and also we provide solutions into vertical markets, for example, into the transportation sector, as I'll mention. And we have a core technology we call Hydra. This is a unique parallel processor engine that we've developed for high bitrate, gigabit bitrate millimeter wave modems. The activities that we're talking about in this presentation are also part of the wider DCMS funded 5G testbed program. We're actually in 2 of those projects, not only in the AutoAir V2X project, but also in the Liverpool L5G project. Commercially, we are deploying our technology in the form of rail qualified products through a partnership that we announced last year with First Group, and the first deployment is just beginning on the South West Rail line, running roughly from Basingstoke up to Clapham Junction. We have a large pool of investors led by ARM, obviously owned by SoftBank, and also Calculus, which is a London-based VC. And as I mentioned, we have a presence in US and Japan. On the right-hand side, you can see some examples of customers and projects. So, for example, you can see the rail application, bottom left-hand corner. This is from a test we did last year at the Network Rail Riddick test centre at Melton Mowbray. Here we see some earlier work with McLaren, with whom we've been partnering on AutoAir, but also on other projects as well. CCS in Cambridge is one of our licensees. They use the modem and radio platform to develop 60 gigahertz mesh nodes for urban and backhaul applications. And this is the block diagram of the IDT baseband chip at map of Liverpool, where we are deploying the millimeter wave technology on the L5G project. And this is one of our prototype nodes that we're developing and deploying, for example, on South West Rail. Okay, as regards the AutoAir project, I think as others have mentioned, we're members of the much larger consortium, including the companies listed here, led by Airspan, DenseAir, but also with Telefonica, so University, ourselves, WS Atkins, Quartus, Wheelwires, Millbrook and McLaren. It's a very large, complex testbed on the Millbrook Proving Ground with many different aspects, both 4G, backhaul, 5G, and in our case, millimeter wave. And our focus is on deploying a high-speed millimeter wave network on the 2-mile circular test track you see on the top right-hand corner here. So we've actually gone through 2 phases of activity on the project. The first phase was 2018-19, where we installed our generation 1 60 gigahertz modems, so-called Typhoon modems, and these date back to 2016 or so, and they operate at 60 gigahertz. And then in the next phase, phase 2, 2019-20, we upgraded that to a full band 57 to 71 gigahertz generation 2 network with much better radio performance and better throughput. And those units are the basis of the products that we're deploying. So that's highly relevant for our commercial activities, and the network is extremely important for us in terms of performance validation. In terms of a bit more detail on the installation, you can see a schematic of the track. We have 11 locations around the track, each with 2 millimeter wave radios looking up and down the track, and then these are connected by fiber to a central garage where we run the network server. We also run the McLaren Atlas data logging and analysis software, and that's a key part of the analytics that we're using to analyze the performance. On the right hand side, you can see that in schematic form. So the vehicle has a dual radio mounted on the roof of the vehicle with connections up and down the track, and the radios themselves also have 2 radios up and down the track. In this particular configuration, we're showing using 2 channels, channel 2, channel 3. As we go around the track, we hand over from one channel to the next as we pass the tower from one zone into the next zone. The data is then fed over the fiber optic cable to the server in the garage, logged, displayed and analysed. So here's some photographs of the installation. So these were taken in the summer of 2019. On the right-hand side, you can see one of the latest Typhoon DN101 SC units. So the phased array antenna sits behind the Blue Wireless logo. So we're using beamforming to make the active connections as the vehicle moves around the track. And then the modem and the network processor, which is a Linux-based software-defined computer, sits inside the box. And then we have power supplies and the data connection, which is terminated in this box at the bottom right-hand corner. So you can see the two radios looking up and down the track on this shot here. Then on the roof of the car, we have what we call the TN, which is short for train network unit. And so again, this is two radios, front and back. And then we have a high-speed PCI digital connection into a network processor, which sits inside the vehicle, rather similar in size to the unit on the right-hand side. Okay, so this is an example of a fairly early result from the Generation 2 testing that was taken in September of 2019. So this was tested at the top end of the band, channel 4 and channel 5, and that's important because at the top end of the band you move away from the oxygen absorption line and you get a much greater range, at least ×2, depending on the channel that you're using. We did this sequence of tests at various high speed speeds, 130, 170, 190 kmph, and in fact we've tested to over 200 kilometers per hour in other circumstances. So the aggregate throughput we achieved was 1.6 gigabits and 3.1 gigabits in this particular set of runs, with an extremely low latency of significantly less than 1 millisecond. And that's to be compared with the latencies we were seeing on the 4G network installed at Millbrook, which is of the order of 50 milliseconds. On the right-hand side here, you see the Atlas traces that were captured during those runs. Starting at the bottom, the staircase is showing each stair on the staircase is showing a transition around one of the access points on the track side. So every repetition is a lap around the 2-mile track. And you can see that we've overlaid the throughput against the speed, 130, 170, 190 kmph. And here we have the signal to noise, which is averaging well over 15 to 20 dBs. And the MCS is a measure of the modulation level on the radio, which in turn generates the throughput. So it's pretty healthy. We see 8, 9s, 10s, and 12s taking up to 16 QAM modulation. On the throughput curves on the bottom, you see that there are some gaps, and they're actually caused by having too much signal power rather than too little. And what happens is the rear radio hangs on too long, and as a consequence, the data rate falls away. So since these results were taken, we've made significant improvements in the middleware, the mobility management software, which controls the association of the radios and when they attach and deattach to the access points. So this is an example of where the Millbrook testing is being vital to help us optimize our solution. As regards McLaren, this is an example of integration with their aggregation product they call the MIG. So this allows multiple data streams to be aggregated end-to-end, including from other data sources such as LTE, and it's typically used in a rail environment to provide on-train Wi-Fi passenger data services. In this particular instance, we're exploring the integration and the upper end of the performance that this solution can deliver. And we also used it to connect a standard Wi-Fi access point so that we can do end-to-end demonstrations and throughput measurements. This particular version is a 1 gigabit Ethernet wide connection, so it's limited to typically 800 megabits of net data. And McLaren are working on the next generation, which will upgrade that to 10 gig in order to improve the speed still further. And you can see here it's installed in the boot of a McLaren 570S car. So we can go as fast as the track can can support during our testing. And on the right hand side, you see the server display in the garage. In terms of throughput, this is a shot taken from the output of the MIG. So we see essentially 2 mmWave connections to the front and rear radios on the car. For reference, at the bottom, you can see the equivalent 4G bumping along the bottom of the curve here. The scale is 1 gigabit here, so typically that's maxed at 800 megs per each of the radios that you can see. And the total end-to-end aggregated data is shown on the top, of the order of 800 megabits of throughput. And again, we're showing the latency of 0.7 to 0.9 milliseconds. We continue to work with McLaren, and recently we've deployed a small test network at a motorsport location in Fontana in California, and this comprised of 3 of our DN101 SCs, the same units deployed at Millbrook, one here, one here, one here, in order to prove that this application would work well in the context of a motorsport application. And that project is ongoing. The project was very successful in terms of demonstrating that this offered much superior performance in this challenging environment compared to other solutions, particularly those based on LTE. The use case here is uploading video from the vehicle to the trackside to improve TV coverage, particularly 4K video. So that's the objective. Moving on to rail, this is not strictly speaking part of the AutoAir project, but it is extremely relevant in that we at Blue Wireless have been using the AutoAir project as a development test vehicle in order to improve, validate, and harden our technology for rail applications. So as I mentioned at the beginning, we're working with First Group, and this talks about the track-to-train rail 5G technology we're developing. In terms of the motivation, what rail passengers want, of course, is much improved Wi-Fi. Anybody who's travelled on UK trains will have seen pretty poor performance on the in-train service, and typically trains today enjoy maybe 10 to 20 megabits per train, whereas the demand is projected to exceed 1 gigabit per train by 2025, if not sooner. And there was a report by Ofcom to the DCMS on how to improve rail connectivity, which recommended using mmWave in order to improve that. So that's essentially what we're doing. We're executing on that vision, and we're using license-exempt mmWave, which means First Group don't have to pay a license to the government to use that spectrum, and also they can dedicate the network, strictly speaking, to their application only and not share it with others through a mobile network connection. The first deployment, as I have also mentioned, is on the South West Rail network between Basingstoke and just south of Clapham Junction to Earlsfield, and this is ongoing right now. This is roughly a 70-kilometre stretch and deployed on something of the order of 300 trains on that main line. We've also deployed in a smaller way on the Isle of Wight, and this is really a proof of concept integration testing test bed, and that's now up and running. Conceptually, it's very similar to the work we did at Millbrook. One small difference is that we deploy two radio nodes on the train at the front and rear of the train, and we do that so that we can overlap coverage from trackside towers, which are up and down the trackside, and improve the resilience and the performance during the mid part of the transition between access points. And once again, we have a trackside network comprising of a fiber layer 2 network into a layer 3 switch, and then onto the web. The units on the right hand side, that's the trackside modem. This time it integrates 2 modems, front and rear, on the white, behind the white panels. These are phased array 57 to 71 gigahertz modems. And then the roof of the train is the TN, which is the same unit we've been testing on the AutoAir project. So these units are being fully qualified to rail standards, EN 50155, and they're going through network rail product acceptance right now. So each unit can support up to 6 gigabps per unit via a 10 gig SFP fiber, and they consume very little power, and thus that places into a good position for efficient deployment alongside on-site rail lines. Okay, so wrapping this up, in our opinion, Millbrook has provided an ideal testbed for development testing of our mmWave high-speed transport technology. The first phase of the project, phase 1 in 2018-19, created the basic testbed, which allows us to basically conduct integration testing and prove that all the systems worked end to end. But that was based on our generation 1 60 gigahertz technology, which wasn't intended for production, but only for prototyping. So phase 2 has been really important for us in terms of being able to deploy production quality hardware with much improved performance and use that to validate and harden our solution for rail and road technology applications, excuse me. So the results from this work have also supported ongoing consultations with Ofcom and in turn CPT in relation to spectrum policy in the 57 to 71 gigahertz band. Perhaps partly as a result of this, CPT have relaxed the rules. They have announced new rules for the licensing of this band, and as of 1st of January, the license rules are rather similar to those applicable to the United States for FCC, and that, in our opinion, will enable this technology to deploy successfully for many applications, including high-speed transport. So the cooperation with Millbrook on testing and McLeod on integration and applications will continue beyond AutoAir, and we're looking forward to working on several exciting projects in that respect. We've also used the AutoAir Millbrook facility to showcase our technology to multiple customers in the rail and road sectors, both locally and internationally. And as far as we're concerned, it's been extremely powerful in increasing our profile, including Mobile World Congress 2019, as well as multiple international conferences and seminars. So thank you very much, and that's all I have to say.
I'm Professor Rahim Tafazolli from University of Surrey 5G Innovation Center, and it's my pleasure to introduce the role and achievements that we had in AutoAir project, which is funded by Department of Digital, Culture, Media and Sport under the 5G Testbed and Trial Program. In collaboration in Work Package 2 5G NR extended trials, it was conducted in collaboration with DCMS and Airspan. It's effectively building upon what we achieved and developed in phase 1 of the project, which is a soft 5G base station, evaluation platform for testing and trialing and optimizing advanced algorithm that can be pave the way for commercial solutions. Our main objectives and achievements in phase 2 of this project was to develop and evaluate new advanced nonlinear MIMO beamforming and detection algorithms that can substantially increase both capacity and number of connectivity using MIMO 5G system. And we developed this unique world first flexible research platform for rapid evaluation, profiling, and advanced algorithms and trials for commercial purpose or contribution to 3GPP 5G standard. So why MIMO system is important is a very key feature in 5G to provide the promised capacity. And traditionally, the linear precoding and detection processing technique has been used for implementation simplicity, But on the other hand, it leaves a lot of unexploited capacity using MIMO system. They can support number of users that in practice are much smaller than the number of the base station antenna systems. And they employ non-iterative MIMO detection that are practical but still far from achievable capacity. What we have done, we developed and tested new massively parallel nonlinear algorithms that you will see later on will overcome all these limitations. At the same time, massively parallel architecture will reduce the processing latency compared to state-of-art linear approaches. Our algorithm can achieve throughput of gains of up to 200% compared to the linear approaches and compare with state-of-art from academia or industry. User connectivity can exceed the number of base station antennas by 200%, even at low signal-to-noise ratio region. Uplink achievable throughput can reach more than 80% of the MIMO theoretical channel capacity limit. In terms of international context from the evaluation platform point of view, there are various software solutions available, but with significant limitation, which doesn't allow us to properly evaluate different algorithms. On the commercial side, AmeriSoft is a very closed source. FlexRAN, no higher layer protocols and mainly physical layer, and no implementation of the user equipment make it challenging to be used as a candidate platform. National Instrument 4G application platform, it doesn't support large or massive MIMO transmission and various functionality for single antenna transmission missing. Open source ORAN, no solution for large massive MIMO transmission and limited single or two antenna functionality is available. Open LTE, no solution for TDD, which is basic structure of the 5G Neo radio, and no support for large massive MIMO transmission. Open Air interface is no solution for large massive MIMO transmission and is not 5G NR compatible yet. Existing software platforms are not suitable for investigation, especially advanced nonlinear approaches. So that's the reason we embark on this activity within AutoAir project. The work, the platform, the unique platform that we have developed, it was published in recently and under the title of Soar Towards a Soft and Open Radio Designed for Rapid Development, Profiling, Validation, and Testing. This shows the setup, the experimental setup, indoor and outdoor, where the UEs can be configured with 2 antennas or 4 antennas, and the base station here is a 3.5 gigahertz, dual polarized 64 antenna elements, monitoring the performance in real time of the massive MIMO, as well as the outdoor setup where UEs communicating a number of UEs with the base station. So on the evaluation platform is 3GPP standard compliant and is quite flexible for testing and validation of breakthrough technologies. It supports different modes of operation for various applications, emulation, near real-time over-the-air or real-time over-the-air. It's modular, built on commercial off-the-shelf devices with software-defined radios and general-purpose processors, and with different profiling for accurate execution execution and measurement of DSP functions. The capability of the platform is, at the moment, we have developed 3 different beamforming algorithms: maximum ratio, transmission and combining, zero forcing, as well as the 5GIC nonlinear solution, MIMO solution, single user, or it can be configured for multi-user MIMO system, up to 4 user equipment, multi-user MIMO, and can be extended to 8 user equipments. Multiple transmission and receiver antennas, up to 16 transceiver antennas, and built-in time division duplex calibration procedure, which up to 16 antenna system can be calibrated. On the speed of the operation of the platform, when we consider a number of sub-functions and algorithms in the air interface, like OFDM demodulation, MIMO detection, demapping, and etc., they all need intensive computation. What we have done, we optimize our platform, which is 45 on the receive side, faster than most of the available technologies to our knowledge, and on the transmit side is 44% faster. And that shows the computation time compared with non-optimized as well as the state of art. The optimized version, which is shown here in orange, compared with non-optimized and equalizers as well as pre-coders techniques that you can see. The test was carried out in indoor as well as outdoor, and you can see the setup of the equipments in the racks of the equipments for indoor and outdoor, and nonlinear 5GIC algorithm employed using uplink soft output multi-sphere, as well as on the downlink Viper algorithm, which is all been published and available in literature. Some of the results of the performance for indoor, as you can see, the uplink gains can be achieved in a real environment up to 150% gain in the spectral efficiency, and this shows the layout of our building with a large number of desks, people moving around, and this is a pictorial image of our indoor, which we shows the plants, the desks, and etc. And 4x4 uplink, you can see the gains that our algorithm provides compared to state-of-art zero forcing. And similarly for 8x4 uplink configuration, on the downlink 4x4, again, we have substantial gains up to 100%, and for 8x4 on the downlink side. So for the outdoor environment, again, we achieve substantial gains for 8x4 and 4x4 multi-user MIMO configuration. And you can see on the uplink side, by 4x4, 90% gains can be obtained. And on the downlink side, 260% compared with the state of art and compared with zero forcing algorithm. And that shows the setup for the outdoor environment, and shows from the picture of the base station looking outdoor, which is the UEs are located from outdoor communicating with the indoor base station. Last, I would like to thank all the team and 5GIC, which is led by Dr. Konstantino Nikitopoulos, and the team members, the main team members, and many people are involved in development of the platform and testing of the platforms. Dr. George Georgios, Marcin Philo, Christopher Husman, Jaya Wardena, and Deluna Decoing, and Alex Thanos. I would like to thank AutoAir members, partners, as well as DCMS and 5G Testbed and trials for allowing us and enabling us to carry out this interesting project, which has many commercial promises for testing advanced algorithms, as well as the platform itself is unique in the market. Thank you very much.
I'm Simon Fletcher, CTO at Real Wireless, and I'll give you a brief presentation on our techno-economic considerations with respect to the AutoAir project. Our focus was on the economic and business case implications, and we have a number of findings with respect to the AutoAir network. Now, Real Wireless is a advisory firm, wireless experts, UK SME. We have two segments to our client base. First of all, the wireless industry, consulting with operators and vendors and regulators and other stakeholders in that industry sector. But importantly for AutoAir, we're involved with clients who we call users, or wireless users, but in the context of 5G, they're called verticals. And in particular, we have a client base in transportation where we've had on a number of occasions, had to appraise the quality of connectivity to vehicles on road or rail. And we are aware that there are some shortcomings in the UK with respect to the performance of that connectivity. And so the AutoAir project probably will fit quite nicely into helping to provide one of the solutions to the problem or the challenges that we currently see. Now, our journey on this particular aspect with respect to transport and 5G started, I would say, with our 2016 activities with the National Infrastructure Commission. We looked at various use cases and the implications in terms of the cost of delivering them, and that was focused on the capital expense relating to the build out of the networks. One of the sectors that we looked at was the transport sector. That information fed into, along with other reports, into the Connected Future report from the National Infrastructure Commission, and they made recommendations on various aspects, but made emphasis on the government role, 5G cities, and also the road and rail as a priority in the next evolution of networks. Now, over time, Real Wireless has been working for road and rail coverage related studies, not just coverage, but also capacity related requirements. And we've established a techno-economic framework that has focused on 4G and advanced 4G and 5G related technologies. So we were happy to bring that knowledge to bear in joining the consortium, the AutoAir consortium, in 2018. And after 2 years of work, we have published our findings in a report as part of the final deliverables of the AutoAir project. Now, AutoAir is interesting in that it's looking at an ultra-dense small cell network, and to subsidize or pay for the infrastructure, we need to take a view as to the value creation, not just looking at the costs to help us establish a business case. But we looked at the in the broadest sense of value creation around safety, environmental benefits and productivity, and that allows us to corral some use cases. We also looked at the implications of the networking platform, the technologies, by working closely in the planning activities for the small cell deployment at Millbrook. So we did the radio planning of the small cell network. We also looked at the backhauling arrangements around mesh. We created a techno-economic model that was scalable to bring or draw out those insights from the Millbrook network into the national UK view. And importantly, we wanted to have a capability to validate our assumptions and extrapolations based on what was happening in the trials activities on the Millbrook testbed. So being able to process the trials data to help with our validation. Now, the neutral host platform is evolving as time passes from a passive model, the DAS or distributed antenna system like architectures of old, into much more of an active system model where the neutral host may deploy small cells and other technologies to support the extension of the mobile operators coverage and provide some edge or close to deployment capabilities that are much more capable than they used to be, going beyond the passive deployment. And a lot of the motivation for that is given through the analysis that's happened through various forums, but the creation of what we call a business enablement layer and a layer which can support new applications. And that active architecture neutral host platform allows for the realization of some of those needs. The challenge for the mobile operators, and it's becoming greater as time goes by, is the capital risk that they see in their business. This is a study we're referencing here from a number of years ago where it was already recognized by discussions with operators that the CapEx-based model, which is technology-driven, is starting to cause some inefficiency of the capital allocation that is seen in the industry. And a way to share the capital risk is necessary for the operators. Now, we wanted to look at value creation. We created 4 categories of use cases. Safety, infotainment, probably well understood at these stages, and there are new use cases emerging there all the time, and they, in particular, infotainment is potentially a high traffic demand creating category. But in terms of value creation, diagnostics and maintenance and fleet services create interesting new use cases and ecosystems of companies in around the logistics and insurance business area that could well create some value over time. So those use cases that sit within those categories, we create a model that allows us to map through from the creating representative views of the roads in the UK to create a demand density that allows us then to create a view as to the small cells that may be required and the capability that may be required capacity-wise to address different traffic demand scenarios. When we are looking at that relatively dense small cell network, there is a cost associated with deploying such a network. We then need to consider the perspective of the MNO, first of all, to see if they had a choice, what would they want to do? How would they extend, for example, their existing macro network? We were able to come to a view as to where we thought the current mobile network would be with respect to the performance that we needed to see for some of the use cases, and we estimated that perhaps 30% of the existing coverage of mobile operators' networks could be, with some further investment around spectrum, could be sufficient to provide the coverage that's required. So additional densification and additional approaches to providing coverage and capacity are needed. When we look at the profile in terms of cash flow for the operators over a 20-year period, we were able to offset those costs in different ways when they take a choice as an operator between a macro build versus a neutral host build. And here, as an illustration, we could see for one of the business case analysis figures that we used, scenarios that we used, we can see that there can be a significant uplift to the cash flow if the operator is able to utilize a neutral host platform in the order here for this scenario of 800 million uplift once you get to a number of years down into the scenario. For the neutral host business model is very sensitive to the efficiency of deployment of the network, and that's where I've just shown some figures here. It's very important to have a favorable access to the road, and just to illustrate the sensitivity here, we have a discounted cash flow looking at the installation time, which is an important metric. If the business can achieve an installation time of around 2 hours per pole or mast for the deployment of the small cell, then over time they are cash flow positive. If they're not achieving that sort of deployment rate when they're required to deploy, and that's due to various issues around the costs related to the access to the roadside, then you can start to see a negative cash flow. So efficiency of deployment important to their cost base, and also access to connectivity such as fiber helps with the cash flow as well. So in value creation terms, the mobile operator sector may see an uplift in revenue if they can provide these services and use cases that we are modelling in the order of over £1 billion per year by the time we're getting into the mid to late 2020s. The neutral host is going to have to do a significant amount of capital investment, of course, to build out their small cell platform. But even for them, our modelling would show that by 2025, 2026 timeframe, if they were to start from year zero now, they would be cash flow positive. Now, the dips in the cash flow here are due to the way in which the infrastructure has to be refreshed, because the small cells have an operational life. If the neutral host is wise in terms of its selection of small cells and has a smart way of refreshing the active equipment, then they may well be able to improve on that sort of cash flow profile. Society benefits are important here for the analysis as well, and we take a view as to the savings in terms of travel times, accident reduction, and CO2 emission reduction by the introduction of some of the use cases, which may lead to tens of millions of benefits just for the SRN, not just taking into account the benefits there may be for other roads, but just for the strategic road network. By 2030, there could be a significant uplift there as well. So the business case, key findings: neutral hosts need to find a complementary way in which they deploy their networks. they need to hit a good occupancy ratio to achieve a successful business model. That means most of the operators, at least 2, need to be occupying their infrastructure. The neutral host models do bring benefits and positive value. The expected revenues do, over some time, surpass the costs, but it's definitely a long-term play for a neutral host on the transport routes. The sensitivity of the model is very much evident around the deployment time and the cost of deployment, and that needs to be taken into account, and they need to be helped for their deployment. Mobile operators, their networks are currently not sufficient to achieve these use cases that we're analysing. If they were to capture the value of the use cases, they may be looking at an uplift as a sector of 800 or so million per annum. The MNOs may expect a 30% gain in their cumulative cash flow over a 20-year period through the adoption of these use cases, and their cash flow becomes positive much quicker if they're employing a neutral host model for the reach of their network. What we were very pleased to see is the narrative coming from the Future Telecoms Infrastructure Review around the market expansion model. I think a lot of our findings will back up the assertions in that study and that report that neutral hosts have an important role to play, and spectrum availability is also important. We modelled a nominal cash flow from the neutral host to the regulator for the utilisation of spectrum, but there are other ways to access spectrum from a neutral host perspective, including them utilising mobile operator spectrum. So our conclusions were the neutral host business model is viable for roads, and we also analysed rail. That's positive as well. AutoAir Testbed has been a good investment in that it's allowed us to validate our models and to take technical data, performance data from the network. We can see that business or market expansion is possible and viable and can be supported through the deployment of these networks and the use cases. And it's enabled us as a company, an SME in the UK, to mature our capability around the techno-economics of coverage, capacity and connectivity on the road and rail network, and this clearly strengthens our business. And as a concluding point, I'd like to make create a big thank you to our partners who have worked with us over the last 2 years, and it's been a very fruitful project for us, and we look forward to working with them again in the future.
Hello again. I'm Peter Claydon, and I've been Director of the AutoAir project over the last 2 years. First, I'd like to thank everyone who's taken part in these presentations on this video, and also for everyone else, and there are probably between 100 and 200 people who've been actively involved in the AutoAir project over its lifetime. I'd just like to summarise now the major achievements of the project over the last 2 years. Firstly, we've proved a technical and economically viable model for a neutral host small cell network deployment in the UK. Now, we proved this for transport corridors, road and rail, but the findings are actually relevant to other sectors as well. So AutoAir members over the last 2 years have been promoting this model to DCMS, Ofcom and others in the UK and indeed internationally, and will continue to do so. And this provides a way in which the UK could actually lead the world in novel forms of 5G deployment, which actually will lead to the true benefits of 5G. Secondly, Blue Wireless and McLaren have made fantastic strides in actually supplying data at high throughputs to trains. And we demonstrated in the project a sustainable 1.6 gigabit per second at 160 miles an hour. Now, we did this at Millbrook, around the high-speed bowl on the high-speed straight. But this is because it's very difficult to actually test these things in a rail application where you may have one transponder on a train which goes past, every few hours. At Millbrook, adjustments can be made to the network and new techniques tested. Now, this has enabled Blue Wireless and McLaren to actually make significant advancements with their customer relationships. And this is a truly world-leading application. Next, Airspan and DenseAir worked with 5G IC at the University of Surrey on optimizing 5G beamforming techniques. Now, this is now an area where the UK can be a true world leader because of the ability to use the hardware that's been developed during the project to test different techniques. It's another area where AutoAir has enabled UK organisations to be true world leaders. And now the future part of AutoAir. We built a sustainable commercial 5G network at Millbrook, and Peter Stoker at the beginning of this video presentation showed how this has already been used commercially. Now, with the relationship between Telefonica, DenseAir and Millbrook, this will become a true 5G commercial testbed over the coming years. And it will be a legacy for the AutoAir project to actually really build upon this. So in summary overall, this project has been a great value for money, with all the money actually being challenged to UK-based companies. And most of these companies are quite small, and it's been a major benefit to them. So with that, thank you all for listening. And we look forward to working with our partners and everyone else involved in this in the future.